Hey guys, so in the last lecture we have seen few examples on the equation of motion of free undamped vibration, in which we found the natural frequency of various systems. First we found for the pendulum, then we found for a semicircular disc uh, lying on the ground. Before that we found a semicircular disc hooked over the center of the diameter. So you've seen also different methods for finding natural frequency or finding the equation of motion and then finding natural frequency. That is Newton's method, energy method, etc. So today we are going to discuss free damped vibration. So what do you mean by free damped vibration? So first, the word free means that this vibration is not forced, so no force is acting on it, so it is moving freely on its own. Now we have seen in the last lecture there is free vibration, but it was not damped, it was undamped. So the damped word has been introduced, a new word. So what is damped? So uh, if the vibration is free, so what will happen to that vibration, that it will oscillate or it will vibrate till infinity, till unless and until a damper or a damp presence is present over there. So if no damper is present over there, then the vibration can continue for unlimited time. So what is damp and what does it do? So first, the definition of a damper vibration, damped vibration. So the energy of a vibratory system is gradually dissipated due to resistance, air. The energy of a vibratory system is gradually dissipated due to resistance. The resistance can be air or fluid. Fluid means air, fluid, liquid. So such vibration is called damped vibration. So what is saying that if there is a pendulum, if it is oscillating from left to right, so after certain amount of time, it will stop oscillating. So why it is stopping? Why it is stopping from oscillation? So it is because of the air. So that air is becoming a resistance. So whenever there is a resistance to the vibration, so that resistance is called damper, which will absorb the energy gradually. So the energy of the vibrator system is gradually dissipated. So it is dissipated due to the resistance. So due to this air, the energy is dissipated slowly and gradually. So that vibration is called damped vibration. So now what are kinds of damping? So we can call there two types of damping, that is active and passive damping. So in active, this refers to that energy dissipation from the system by external means. So that is like controlled actuator or something directly. And passive means this refers to that energy dissipation within the structure by adding a damping devices like accelerator, structure joints and supports. So for for meaning that if any vibration, any equipment or any machine is getting vibrated. So if you directly act on that machine or the vibratory part, it is collective, but instead of acting on that vibratory part, you use a damper or any other anti vibratory part like spring or isolator to to reduce the effect of that vibration in negative. It is then it is called passive. So these are types of damping. So these are like types means active and passive. So we will see various types of damping in detail. So first damping will be dry friction. We can call it dry friction, or it can also be called as Coulomb damping. So this occurs when two machine parts rub against each other in dry or unlubricated surfaces. So in this, the resistance is direct metal to metal contact. So it will collide to it, and it will store. It will just dissipate the energy, and it will just various forces will act on it. So this is dry frictional Coulomb damping. Then second, this is the most important. It is viscous damping. Viscous damping, and this damping we will use this damping concept we will use in further uh, examples or in further study. So what is viscous damping? So this occurs when system vibrates in a viscous medium. So what is viscous medium means? Any fluid like oil or what oil or honey which is very viscous, so in which there is a high viscosity. So in that medium, if any system is vibrating, so that vibration can be absorbed by the medium. So damping resistance, it is damping resistance, that is, let's say the damping resistance, we call it at C. So damping resistance is directly proportional, sorry, let me call it as uh, so here the damping resistance is directly proportional. So let's call the damping resistance force uh, FD. Damping resistance force is directly proportional to its velocity. So velocity we generally denote here as x dot. So during the damping action is called viscous damping. So this is called viscous damping. So if I remove the proportionality sign, so I will get F d. F is equal to C into x dot. So now there is a constant which we will call it as damping coefficient. So this we will call it as damping coefficient. Damping coefficient. So if I have to define this damping coefficient C, so what it will be? So it will be C equal to FD by x dot. So let's define the damping coefficient C. So the damping coefficient can be defined as the ratio of damping force per unit velocity. So now this is a very important equation which we will use again and again in further study. So this is very important. We need to remember this equation. So this or this any of one, and we can derive it. So this damping force is equal to C into x dot. So this is the equation of damping force. So now we will take an example of a fluid dashpot to consider, so to understand the viscous damping. So this is an example of viscous damping, but need not to consider that this is the damping, this is only the damping. So let's consider fluid dashpot. So let me draw a piston cylinder arrangement. So suppose this is the piston, this is cylinder, and suppose this is the rod. So this consists of a piston moving inside a cylinder filled with a viscous fluid. So suppose there's a viscous fluid inside this. So now suppose the distance between the piston and a cylinder, there's a clearance of E, distance E. So this E is a clearance, and the viscosity of this fluid is suppose mu, and suppose the mean diameter is dm. The mean diameter of this cylinder is dm. So the damping action occurs due to this following, due to these reasons, that damping due to the drag of the fluid. So as this piston will move down, so the fluid will move up and it will drag back the piston. So this fluid moving up will drag it. So damping action can occur due to this. Damping produced by the flow of the fluid through the clearance space. So when the fluid is flowing through this clearance space, damping is produced due to this. And damping produced due to the pressure difference on the two sides of the piston, because there will be a pressure difference, because there will be low pressure, high pressure, because there is a fluid more here, less here. So due to this pressure difference also damping can be produced. So if I want to find the value of C here, so what will be the value of C? If the clearance is small, the first two components can be neglected. So C, the value of C will be equal to 12 mu. Mu is viscosity divided by pi into uh, dm, this is mean diameter, into E cube, that is clearance. H, now what is H? So H is the height of the piston, and AP. So what is AP? So AP is area of the piston, so that we can calculate with the help of pi by 4 d square. So this is the formula. So assumptions which we have taken, which has to be taken before deriving this equation, is that piston cylinder are concentric, means the center line, it is the center axis of this piston and the cylinder are both the same. The damping medium considered as a perfect fluid. So this is considered as a perfect fluid which follows the Newton's law of viscosity. It is called a perfect fluid. And piston rod diameter is small compared to the piston diameter, means this diameter is small compared to this diameter. So it is obvious. and a sharp orifice effect is neglected. And here the orifice effect is neglected. Sorry, not here. Sorry, here the orifice effect, that fluid move, so that is neglected. And the flow of the fluid is laminar. So when the flow is flowing, it is laminar and not turbulent. So this various assumptions has been taken for deriving this equation. But this is an example of a piston cylinder, but we will use generally for any damper, we will use this equation, and we will use the symbol based on this fluid dashpot as this as a damper. So this symbol we will use as a damper for any given damper. So this symbol of fluid dashpot we will use for further study. So so there is another kind of damper, that is an eddy current damper. So this I will not use generally, but just for information. There's an eddy current damper. So here the only the principle of eddy current has been used. So as we know that there's two poles, magnetic poles is north and south, and if we move a plate in between this north and south pole, then eddy current is being generated. So as the rectangular plate moves between north and south pole of the magnet, the current is induced in this rectangular plate, which is in form of eddies and set up a magnetic field. So this will set up a magnetic field in the direction opposing the magnetic field. So this is a case of damping. So now we will see the equation of motion of a viscous damper. So equation of motion for viscous damper. Now I will draw a spring mass damper system. So that is a spring mass and damper, having spring having stiffness K, damper having damping coefficient C, and mass M. Now this is a three parts of the vibratory motion. So this the equation which we'll get will be similar to the RLC circuit, that is resistance, inductance, and capacitance circuit, where we have three components. So similarly, there is three components of the vibrator system. There are three components of the electrical system, in which we get some equation. So similarly, we will get a similar kind of equation here. So before solving this, we will use the Newton's method. So similarly, we will find the forces acting on the mass, and we will compare or we will equate with the inertia force, because according to Newton's law, that each and every action has equal and opposite reaction. So the net force will be equal to some inertia force. So the net force should be equal to 0. So if I draw a free body diagram, so suppose this is mass M. So as usual the weight force will act uh, in sorry so there are two forces. So first, uh, this spring force. So spring force will act in a upward direction, so that is k into x. And there is a damping force, so damping force will act in upward direction, that is c x dot. So now there is no force to balance these two forces, so the inertia force will act in downward direction, so that will be m x double dot. So if I take downward as positive and upward as negative, so I can write that inertia force is equal to sum of all external forces. So external forces are kx minus cx dot, and inertia force is mx double dot. So if I bring this negative terms on the left hand side, so I will get mx double dot plus cx dot plus kx is equal to 0. If I divide the whole equation by m, so I will get x double dot plus c by m x dot plus k x by m is equal to 0. So now here x double dot is acceleration, x dot is velocity, and x is distance. So now this is the equation of motion for damped free damped vibration. So now we can solve this equation and we can find the solution of this equation. So it will take a long time, so this we'll see in the next lecture. So now this is the equation of motion for the damped vibration. I hope you understood this equation. So thank you very much.